All right, welcome back, everyone. It's a rainy, kind of mild Friday in Newark, Delaware today. Gray, but still pretty mild for December. So I welcome you back. As usual, I'll open the lecture with any questions or comments or discussions that anyone has. Okay. So we're winding down. I think we're going to finish up with phase equilibria. And I'm going to try to get into chemical potentials of non-ideal systems, since chemical potentials are so important. So that would probably be my goal for the rest of the semester and what to complete. Because once you understand chemical potentials, everything else is a matter of just writing equations down for chemical potentials and then just doing whatever you have to do for your specific system. So today, I'm going to finish up our phase diagram for binary systems. We have two components, two chemical species, and two phases. And since chemistry is usually thought of as liquid vapor in the solution, though this is a very limited scope, but it's a good place to start for looking at multi-component binary systems in liquid vapor equilibrium. So where we ended up last class, let me remind you that the system we have, of course, is a liquid and in equilibrium with vapor, and of course at the microscopic level, microscopic meaning angstrom level, we have molecules that are moving back and forth due to their kinetic energy from the liquid and the vapor phase. And this is a consequence of the fact that the chemical potentials of any molecule in the liquid and the vapor are equivalent. And so if we specify a particular temperature, okay, so temperature is constant, we know that the pressure now in the system is going to be one value, okay? We can't have the liquid be one pressure and the vapor be another pressure. They both have to be at the same pressure, okay? So, well, let me go back. Let me just, well, I can continue this. So we know that once we specify temperature in the system, if we don't specify all of the compositions, the pressure must be same in both phases. Okay, we can't have anything that's different. Otherwise, again, we would have a non-equilibrium system, right? If you don't have the same, because you can imagine if the vapor has one pressure and the liquid has another pressure, as you get to that interface, right at that interface, you're going to have a discontinuity, right? It's a very huge discontinuity if the pressures are different. It doesn't take much to have a discontinuity, and that's non-equilibrium. So that really can't be. So the pressures in both phases have to be equal. So this is obvious perhaps, but P liquid must equal, okay, this is must, the pressure of the vapor. Okay, so in the vapor we have A and B, both are volatile. In the liquid we have A and B, and we have YA and YB, and we have XA and XB in the liquid phase, and the sum of the mole fractions is, as always, 1. So the question we were after last class, okay, is what is the dependence of the total pressure in the system vary with the composition with liquid and vapor phase composition. Okay, and really that's P total. How does that determine, how is that determined by X, A, Y? And of course, we specify T, okay? So the question was, what is P total as a function, right? The pressure is going to be represented as some mathematical function, or we can represent it as a curve. And it's going to be dependent on YA, XA, and T. T is specified. So now it is upon us to discuss how we get it how we determine P total as a function of the compositions. And at the end of last class, by assuming that the liquid and vapor are ideal, okay, so the vapor is a gas, ideal system of ideal gases, and the liquid is ideal. And by ideal liquid, what I mean is that the interactions, okay, whatever those they may be, I'm not sure how in depth you've been introduced to interactions, but the notion of an interaction really requires quantum mechanics. And so in an ideal world, we would teach quantum mechanics before thermodynamics, or maybe simultaneously, but we don't. But in any case, whatever your notion or perception of an interaction is, an ideal liquid is one in which the interactions, of course, have to be considered, unlike an ideal vapor or an ideal gas, where one can reasonably say or assume that there are no interactions. To say that there are no interactions between particles in an ideal vapor or ideal gas is not that far of a stretch. But of course, the whole point of a liquid is that you have strong interactions, right? Otherwise, you wouldn't have this change from a vapor to a liquid. So when we discuss ideal liquids, we really can't say that there are no interactions between the components in an ideal liquid, because we wouldn't have a liquid, okay? So this is something perhaps that you've not thought about, but in an ideal liquid then, what do we mean by ideal liquid? And what we mean is that the interactions, whatever your notion of those that may be at the moment, we haven't quantified it yet. Those interactions between different particles in the system are equivalent. So in this case, since we have two components, A and B, the interactions between A and A are equal to the interactions between B and B, meaning that AA interactions, BB interactions, and AB interactions are all equal. Okay, so if I'm a particle or a molecule of A, the way I interact, whatever that means, okay, whatever physical phenomenon that is involved in this interaction, whether it be a Coulomb interaction, something that's a dipole interaction, instantaneous dipoles, a magnetic interaction. The interaction I have with another A molecule is the same as I would have with a B molecule. So there's, again, so as an A molecule, I really can distinguish between A and B, other A's and B's. That's what it means to be an ideal liquid. And so this is more or less things like if you mix alkanes, they're okay, but they would form an ideal solution. They're nonpolar substances, but if you were to mix an alkane and water, for instance, there you know that the interactions are much, much different. So alkanes interact by nonpolar interactions or instantaneous polar dipole moment interactions, whereas water is strongly polar. So the interactions between water molecules are much different than the interaction between a water and an alkane molecule. So that's why you see here that alkane or organic and water systems are not ideal. They're quite non-ideal. So that's what I mean by a liquid that is ideal. Okay, so given that we have an ideal liquid and an ideal vapor, we saw that the total pressure, and I'm not going to go through the derivation, I posted the notes, but the total pressure as a function of XA, okay, which is the liquid phase composition. I haven't said anything. So we've taken care of temperature because we specified it. And so last class we said, all right, well, now we know how the total pressure varies with the liquid composition. And so if we say that XA is 0 here and XA is equal to 1, we saw that the total pressure curve, and it turns out to be linear, it's a line, is this, okay? And so we know that if we increase, so anywhere along this line, we have coexistence of liquid and vapor phases, okay? Now, if we go above that line, at any composition, we have all liquid. We have all liquid okay, but it's still a mixture. Of course, not at the endpoints because there the mole fraction of one species goes to 0, but anywhere along that line, we still have a mixture of A and B. Okay. So what this told us was part of the phase diagram that up here we have liquid, and if we start at any point in that system or at that total pressure and composition, if we were to lower the pressure, so let's say we started here and we lowered the pressure, at some point we would hit conditions where we would start forming vapor. Okay? And so this is the point at this pressure, at this composition. Okay, we start at a particular composition and we come down by lowering the pressure. Okay? Once we lower that pressure until we hit that line, we get vapor. Okay, so what this is telling me is the composition of the liquid. Okay, I still have liquid and vapor. Once I hit that line, I have two phases. Okay, so let me make sure everyone understands. If I start here, I only have all liquid, and now I'm going to start lowering, and that composition is going to be X sub A, whatever that composition is of that liquid. And I'm going to keep the temperature constant. I'm going to keep the composition constant, and I'm just going to lower the pressure. Okay, I'm just going to move vertically down. Okay, so it's going to be all liquid, all liquid, all liquid, all liquid until I hit that line. And then when we hit that line, we all know now that we have to have two-phase coexistence. Okay, we have two phases in coexistence once we hit that line from above. Okay, and that's this point here I just circled. And we know now that the composition of the liquid phase in that coexistence system is given by the composition that we started with because we didn't change it. So that composition, you can say is X sub A naught. Okay, it's just some variable. There's nothing important to it. It's just X sub A naught. Okay, but that doesn't tell us anything about what the composition of the vapor phase is. Remember, at that point, at this point, we have both liquid and vapor because we're on the line. We know what the composition of the liquid is. It's given by the x-axis, and we've only used X sub A right now, so that's fine. But we don't know what the composition of the vapor is. Okay, that's still a mystery, and that's now what we have to set out to find. How are we going to represent the composition of the vapor at this pressure? Okay, that thing. All right, so that's the goal, and so now we're going to proceed. I just recall that we have an ideal gas and an ideal liquid. So in that case, P total, right, is going to equal the partial pressure of A plus the partial pressure of B. Okay, this is because we have ideal vapor, ideal gas. Okay. And because we have ideal liquid, we can use Raoult's law, which is this relationship. PA is equal to the mole fraction of A in the liquid. Remember, this is the liquid times the vapor pressure of A, which I call the saturation pressure at the temperature of interest because we've specified temperature. Again, we have an analogous relation for B. Okay, and so these represent ideal liquid via Raoult's law. Okay, any questions? Okay, very good. So now let's take a look at what happens for YA. And that's very simple. All right, so we can start with P total is equal to the partial pressure of A over Y sub A, because we know that P sub A, if we were to look in just the, right, this is for ideal gases. Okay, that we know from a long, long time ago. So P total is equal to PA over YA. But we can now pick what expression we want to use for PA, the partial pressure of A. So actually, let's start with X sub A, our Raoult's law expression, PA sat over Y sub A. Okay. And so we know that the total pressure, which is really what this is all about, which that's on the left-hand side, the very left-hand side, P total is going to be PA plus PB. We know that PA is this and PB is this. So what we do is write PA as XA, PA sat, and we write PB as XB times PB sat, which is the vapor pressure at the temperature of interest. Okay? And so now we have these two relations right here. Okay? This part of our discussion of the total pressure. Again, this is all total pressure. Okay, and so we're going to use this now, this expression. Okay, we're going to use we'll use this to determine x sub A as a function of y sub A. Okay, we're going to do that intermediately. And that's then going to allow us to figure out what P total is as a function of y sub A, because we already know P total as a function of x sub A. If we know what x sub A is as a function of y sub A, we can easily find the total pressure as a function of y sub A. Okay, so let's do that. And let's see what we get. All right. So we can now, this is really just all algebra. Okay, this is all just algebra. So we'll start with this expression. Okay, and we have x sub A times PA saturation is equal to, so we're going to multiply through by y of A. So we'll have y of A, x of A times PA vapor, the saturation, plus y of B times x of B. Okay, but we know that x of B is just 1 minus x of A. So this is going to be y of A times 1 minus x of A times P B sat. And so all I've done is multiply this expression by y sub A, okay? Because, and I've isolated x sub A times PA sat on the left-hand side. And of course, xb is just 1 minus xa, so I made that substitution. And now I can just multiply everything out. So xa times PA sat, which is what I have on the left, is equal to ya xa PA sat of t. And here I have, if I multiply through everything, through the 1 minus xa, I'm going to have PB times ya. So this will be ya times PB. Okay, and then I'm going to have a minus ya xa times PB sat. T. Okay, this is all algebra at this point, nothing fancy. All right, so now we're going to do, let's see, we're going to sort of isolate a few more things, just rearrange. So I'm going to bring some terms over and I'm going to leave one term on the right-hand side. Okay, and this is the term I will leave on the right-hand side, right here, and I'll bring everything else to the left-hand side. So that will give me xa PA sat minus ya xa PA sat t plus ya xa PB sat of t is equal to ya PB sat. Okay, so again, we only left the ya times P vapor pressure of B on the right-hand side. And then it seems like there's an XA term on, there's an XA in all of the terms on the left-hand side. So I'm going to factor that XA out. So that's going to give me XA times PA sat T minus YA times PA sat plus YA times PB sat. And that's all equal to YA times PB sat. Okay. All right, now let's see what we can do here. So we bring down the x of a. Okay. So there must be some way to combine all of the terms in this expression. So let's see what we can do here. There's a PA sat and a PB sat. Right? And there are two terms with a PA sat. Okay. So, and there's only one term with a PB sat. So let's keep that one term here. So that's going to be YA times PB sat. And then we have here remaining this term and this term both have a PA sat, which we can factor out. And once we factor the PA sat out, we have 1 minus YA, which is just YB. Okay. So this will give us YB times PA. And that's equal to YA times PB sat of T. Okay. And so now we can solve for x of a. It seems like the only place we have an x of a is on the left, and everything else is in terms of y sub a. Okay, and remember, our goal was to get x of a in terms of y sub a. Okay, so we can do that now by just solving this expression for x of a. So x of a becomes y sub a times PB sat. It's just a lot of algebra, that's all. Divided by this thing in the brackets, which is YA PB sat plus YB times PA sat. Okay, so that gives us x of a as a function of y sub a. Remember, the PB sat and the PA sat are just constants once we specify a temperature T. Right, so so this gives us x sub a as a function of y sub a. Okay, any questions? It's just a lot of algebra, that's all. So now we go back to our expression for the total pressure. P total, right? We can write this as the partial pressure of A over y sub a, right? We call for an ideal gas, the partial pressure is just the mole fraction of A times P total. So if we multiply both sides of this by YA, we get our expression for the ideal gas, which is given right here. Okay, so all I did here was isolate P total by dividing through by YA. So we have this expression. And so we know what PA is from Raoult's law. PA is just XA times PA sat of T divided by YA. Okay. And we now know what X of A is in terms of Y sub A. It's given by the expression in the circle. Okay. It's given by the expression in the circle. We have X sub A on the left and everything on the right is in terms of Y sub A. So all we have to do is substitute for X sub A. Okay. So what we're going to do is substitute this expression for X sub A. And I'm going to have this PA sat over YA multiplying everything. Okay. So essentially I have PA sat over YA multiplying whatever is in this circle. Okay, and you can see what that's going to give you just by looking at what I just did here. Okay, so the Y in the numerator, the YA is going to cancel because I'm multiplying whatever's in the circle by PA sat divided by YA. So that YA is going to cancel the numerator, right? The YA in the numerator, and then all I have left with is a PA sat for the numerator. So this is just going to be PA sat of T, PB sat of T divided by, and I don't have to worry about anything on the bottom. I just bring down whatever I had in the denominator in the circle. So this just gives me YA times PB sat plus YB times PA sat, where again, the PA sats are the vapor pressures, okay, at this temperature. Okay, and so we know now that YB is just 1 minus YA. Okay, so YB is just 1 minus YA. So we have then P total now in terms of YA. So now we have P total in terms of YA. There's no X sub A here, okay? We used our our knowledge of what it means to be an ideal vapor and ideal liquid to arrive at this. Okay. So we have here now then, this is going to be PA sat of T, PB sat of T divided by YA, okay, PB sat plus 1 minus YA times PA sat. And so that's what we have here for the P total, the total pressure, okay, in terms of Y sub A. And this P total is the same as the P total that we obtained using X sub A. Okay. So this is P total. Now X sub A, Y sub A, and T. That's what we were after at the beginning of this whole discussion. Let me see if I can, right here. That's what we were after. Okay. P total as a function of X sub A, Y sub A, and T. Well, we already found the X sub A dependence last class. And so now we just found the Y sub A dependence here. Okay. Independently, but it doesn't matter. We can choose to, and these two P totals are the same. So the P total that we derived last class is the same as this P total. They're not different. They can't be different because the system is in equilibrium. Okay, so let's think about this. When we have Y sub A 0, when Y sub A is 0, meaning that we only have B in our system, so that we're going to be at one of the endpoints in our curve. Okay, when Y sub A is 0, this term is going to vanish in the numerator. Denominator. And the 1 minus YA term is just going to be 1 because Y sub A is 0. So that 1 is going to multiply PA sat, and that PA sat in the denominator will cancel the PA sat in the numerator, and all we're going to be left with is PB sat. So for YA equal to 0, P total is equal to PB sat at this temperature, and that's what we found last time. Okay, that's what this guy was. When Y sub A is 0, okay, this guy has to be the vapor pressure of pure B, and that's what we get. And you'll see that if you go to YA equal to 1, this is going to be the vapor pressure of pure A. Okay, and you can see that from this expression, when Y sub A is equal to 1, the second term here is going to cancel because 1 minus YA, which is 1 minus 1, this gives you 0. YA is 1, so that's going to multiply PB sat. And so the PB sats cancel in the numerator and the denominator, giving us P total is equal to PA sat. And that's, of course, what we would expect because our system only has A at that composition. So that's kind of obvious. We already saw this, and this is sort of a self-consistency check. Everything works out at the endpoint, so that's very positive. Okay. Now, we can actually massage this expression to collect for P total to collect Y sub A. So let me just write that. Maybe it's a little bit more insightful to some of you. Okay. So I'm going to have everything that has a YA together. So this will be YA times PB sat minus PA sat plus PA sat of T. So all I did here was take the denominator in this expression, okay, and collect all the terms that have a Y sub A. Okay, and so that's why I did that. So what this tells us is that this is a function essentially of some constant divided by, let's say if we wanted to write this as some function of Q, right? So Q is our independent variable. I'm doing this to show you what the form of this function would look like. So let's say Q is some independent variable and f of Q is some function that depends on Q, okay? Well, this will just give us a constant in the top because we know the set vapor pressures are constants. And then this is going to give us Q, which is YA. In this case, YA is going to be our independent variable. So it's just going to be Q times some constant, which is another constant, plus another constant. So let's say this is constant 3, this is constant 2, and this is constant 1. So what we see here, that f of q, right, is something that is going as 1 over q plus a constant. Okay, so mathematical form of this expression as a function of YA is given by this. This is the mathematical form. Okay, so it allows us to see what that curve looks like. And what we see here is that it's not linear. So P total versus Y sub A is not linear. Okay, and as opposed to what it was for P total as a function of X sub A. So really P total goes as 1 over Y sub A, okay, plus a constant. Okay, so that's what we see here in this expression. P total goes over some constant, so we're not really worried about that. We're worried about the mathematical form of this function, which is really 1 over YA times a constant plus another constant. So it's just 1 over YA plus a constant. Okay, and this is not linear. This is not definitely linear. Definitely not linear. And so what does it look like? Well, we can go back now and plot P total, and I'll just make another plot. Okay, so now we're going to add everything together. Here's P total. Now we know that we have XA and Y sub A. Now we're going to plot everything together. Okay, so here X sub A is equal to 0, Y sub A is equal to 0, X sub A is equal to 1, Y sub A is equal to 1. T is specified. Okay. And we know that the liquid part of this curve is going to be given by this. I overshot, but it's okay. Okay. So here's PA sat at this T, and here's PB sat. Oops. Okay, and we saw that up here is all liquid because we have high pressure. Anything along the line is a coexistence. So now we have to plot P total as a function of YA. So this curve is P total at coexistence as a function of XA. Okay. And P total of YA, it turns out, in this case, is going to look like this. I'll make it this color. Okay, it's not linear. Let me make it a little bit better. It's not linear. It's hard to draw these things. Okay, that's good. So it's non-linear. Right, so this is P total as a function of YA, okay, which is what we just derived. All right, so any questions on this? Okay, so this is all liquid up here. It's still a mixture, don't forget. It has to be because we have composition on the x-axis. So anything that you represent here is going to be a mixture, except for at the endpoints. Okay, so now let's think about this. Let's start here. This is going to be our initial point. Yeah, that's good. So let's start here, okay. So we have our initial point. Okay. And what we're going to do is lower the pressure. So at this point, we have some initial composition. We're going to start in the all liquid phase. Remember, this is all liquid. So we're going to start at that X point. We're going to have some X sub A naught. So remember, this is all in terms of compositions of A. B is simple. You just subtract 1 minus whatever. So this is going to be X sub A naught. And what we're going to do is move down by reducing the pressure. So we're starting in the all liquid regime. We still have a mixture. The mixture has a composition XA naught and XB naught, okay, in that liquid phase. Now we're going to start decreasing the pressure on this liquid. Okay, so we're going to go vertically down, okay, until we hit this point, which is on the line. And we saw that on the line, we're still represent that line is for the liquid. Okay, so at that line, we have now the first instance of liquid vapor coexistence. This is the first existence of liquid vapor coexistence. We're forming that first amount of vapor as we reduce the pressure from in our system, which was initially all liquid. Okay, so when we hit that black dot, which is on the line, we've now started making vapor. Okay, so now we have liquid and vapor in coexistence. In fact, we may have bubbles. Okay, so we may have bubbles. You might start seeing bubbles in your liquid, and those bubbles are the vapor. Okay, and those bubbles are now going to like flow up to the surface, the interface, and then they're going to try to make a vapor phase. Okay, so you're going to form these bubbles. Often this is called a bubble point in the phase diagram. So this line is the bubble line. So if you start in the liquid, you decrease the pressure. Once you hit that line, you're going to form bubbles. Okay, so sometimes this thing is called the bubble line. The bubble line or the bubble curve. All right. So you've started making this system, but you don't know what the vapor composition is. So you started with all liquid, there were no bubbles in it, it was all great, you know, it was all chill. You started decreasing the pressure, and all of a sudden you see bubbles. Okay, it's your second phase, the vapor phase. You know, like, whoa, wait a second. I know what the composition of the liquid is because I started with a particular composition in the liquid and I didn't move along the x-axis. So that composition of the liquid has to be what I started with. But what's the composition of the vapor? Okay. What's the composition of the vapor? Well, here we have to seek recourse in the fact that we know that both the liquid and the vapor have to be at the same pressure. You can't have the liquid being at one pressure and the vapor being at a different pressure. They have to be at the same total pressure. Okay. So we need to know P total as a function of both X sub A and Y sub A. Once we hit that line, we've already seen that that line is P total as a function of X sub A, so we know what X sub A is. But now that line represents the liquid. And if we want to know the vapor composition, we need to know how to get to the line or the curve that represents the vapor composition. And that's quite simple because we know once we hit this point right here, okay, the line represents the liquid composition and the vapor has to be at the same total pressure. So we got to hit some other curve at that same pressure. Okay, we have to hit some other curve at that same pressure. So now we go horizontally and see if we're going to hit any other curve, okay, at that pressure. And it turns out that if we go to higher values of Y sub A or X sub A, if we go towards the right in this curve, we are going to hit in this graph, we are going to hit another curve. And that curve is going to be the curve that represents P total as a function of Y sub A. So what you do is you just go at the same pressure because we know we can't have different pressures. And so this is supposed to be a straight line, and we hit this point. And that point now represents P total as a function of Y sub A. Not X sub A, Y sub A. But we know that Y sub A, based on our convention, represents compositions of the vapor. And so now we know what the composition of the vapor is at this P total. Okay. So this is the composition then. Let's see. Yeah, we still have X sub A naught, but this will be Y sub A naught. All right, so did everyone follow that up to this point?
Yes.
Okay, the crucial point here, right, is if you start, once you hit one of those lines, okay, both of those lines represent liquid and vapor coexistence. Okay, they both represent liquid vapor coexistence. However, okay, one line gives you the composition of the liquid and one line gives you the composition of the vapor. Okay? That's why you have to have these two lines. Okay? So, and we know the connecting thing is that the total pressure has to be the same in both phases. And that is the important thing. That's what connects everything. Okay? So if you have liquid vapor coexistence and you want to know the compositions of the liquid and the vapor, you have to use those two curves, okay, at liquid vapor coexistence. And the 2 points that you read off of the two curves have to be at the same total pressure. They have to be, otherwise you wouldn't be at equilibrium, right? You can't have one thing at a different pressure. Okay. So now, if you start moving this black dot to, let's say, this point, which is now red, okay? Now you're gonna, so what you've done is start with your all liquid pressure and you've reduced it. You got to the point where you started forming bubbles and you see bubbles now, okay? And you've kept reducing the pressure. There's nothing that says you can't reduce the pressure. You just keep reducing the pressure, keep reducing the pressure. And what you're gonna find is that more bubbles will form, more bubbles will form. And now you'll see that some of these bubbles will take up volume in your system, and you'll have a vapor phase that's above the liquid. Okay, so you still have, now it will be much more discernible. It won't be just bubbles like you're boiling something, but in fact, you'll see a vapor phase in the container, in the vessel, that is above the liquid phase. Okay, so it's still two-phase, okay, but now that vapor phase becomes more discernible, more distinguishable. Okay, well now, wait a second, we're not on any line. Okay, we're not on any line. Okay, we're in the middle of these two lines. Okay, so what are we going to figure out? Well, so we know we have coexistence, okay, but we're not on a line. So how are we going to read off what the compositions are of the liquid and the vapor? Well, to do that, again, we know that the two phases have to be at the same pressure. Okay, so we just move horizontally until we hit the appropriate curves. So in this case, right, if we move horizontally this way, we'll hit this curve. We'll hit this guy. And if we move horizontally the other way, we'll hit this guy. And those two dots, okay, are going to represent, I'll represent them with triangles. Dots and triangles. Those are going to represent the liquid and vapor compositions once we reduce that P total to the value that's shown by that red dot, if you read it across. And so now we know then that this guy is going to be X sub A1, and this guy is going to be Y sub A1. Remember that the X-axis has both X and Y. Just depending on which curve you read, okay, you either have Y or you have X. So that straight line, if you read anything using that, so if you drop lines down from that straight line to the X-axis, you're going to be reading X. And if you drop straight lines down from that curved line, you're going to be reading Y. Okay, so that's what that means. All right? Any questions? Was that clear? Or do you understand that how we got that? Okay. I don't hear any objections, so I'm going to take it that everyone's got it. And now finally, we're going to end up by reducing the pressure till we get to this point right here. Okay, so we, again, and now it seems like we've hit another boundary, because now it seems like we're on the curve that gives us P total as a function of Y sub A. Excuse me, throat is getting dry. Right, so we're on this curve now that gives us P total as a function of Y sub A. Okay, so at this point, what we started with was all liquid. We started reducing the pressure. We got to a point which is that red point, And there are many other in-between points, but that red point is the one I picked, where we have discernible, a liquid and a vapor phase that are discernible. You would actually see, so if you had a container, okay, initially it would be all full of liquid. And as I decrease the pressure, you'd gradually see bubbles form when you hit that line. And then as you kept decreasing the pressure, you'd see that there would now be a vapor phase above the liquid. Okay. Now what we're saying is we're going to keep reducing the pressure. We're going to keep reducing the pressure, keep reducing the pressure in our system. And all of a sudden, when you get to that last point, this point, what you're going to have is essentially all vapor, and you might have a few droplets. You might have some droplets hanging around. Okay, so you have mostly all vapor in this container, and you're going to have droplets. You might see droplets all over the place. Okay, so you still have vapor, which is the predominant phase, okay, in coexistence now with liquid, which is the less predominant phase. It's the minor phase. When we were coming down, we saw that the liquid was the dominant phase, and now we were getting bubbles, which is the minor phase. But now we've transitioned all the way from liquid to vapor, and so we have these last remnants of droplets of liquid. Okay, and sometimes people, if you get up early in the morning, if you look at the grass or the leaves, right, what you see on these things, on these not so warm summer days, is dew. You see dew, and so this line is called, appropriately, the dew line. Okay, because what you would see in the containers, it looks like dew, droplets of dew. Okay, and so at this point, you know that the composition of the vapor is going to be given by what's on the purple line, that curve. Okay, it turns out that it's really just x sub a naught, remember? And that makes sense because if you started with all liquid, which was a composition x sub a naught, and now you transition it to all vapor, the vapor is going to have the same composition, right? Since you started, because you can't annihilate mass, you can't destroy or create it. So whatever you had as your composition just carries through. And so at this point, y sub a is just y sub a naught. You just switched x sub a to x sub a naught for y sub a naught, or vice versa. But if you want to know what the composition of those the droplets is, right, that dew that's still hanging around at this pressure, all you have to do is understand that the total pressure is the same in both the vapor and the liquid, and then you just read horizontally across until you hit the appropriate curve. And in this case, opposite of what we did when we were coming down from the top, what we find is that if we go horizontally from this guy, it's kind of hard to see perhaps, but you'll hit a point here on the curve for, it's not, again, it's not pure B, it's not x sub a 0, it's just, that's the way it kind of turned out, but it's not at 0. So you have some non-zero composition. Let me just erase that. And so at this point, you will have the composition x sub a 2. Okay, and that's going to correspond to your final composition when you've turned all of the liquid to all of the vapor. So was that last part clear? Any discussion? People needing discussion? Okay, and now if we start at this point, right, and keep decreasing the pressure, what's going to happen? What's going to be left? Anyone want to take a guess? Now I'm just going to keep going the pressure.
All in vapor phase.
Yep. So, yep, that's exactly right, Sheldon. And so what that means is that everything on the bottom of that curve, that purple curve, is all vapor. So that's the all vapor regime of our phase diagram. It's still a mixture. It's still a mixture, remember, but it's all vapor. Analogous to what we had at the top, which is all liquid, but still a mixture. Any questions? So this is how we read these binary two phase diagrams. We have to connect the compositions. We know we have two species and we have two phases, right? And we're interested in the composition. We're really, we have to be, because um, if you're making something, you want to know the composition, right? And in this case, it's kind of interesting that we started here, right? But we enriched one of the phases in A, and we decreased the amount of one of the phases in terms of A. You see here that the vapor phase, if we're looking at this coexistence curve, so right here, we saw that the composition of A in the vapor phase is much higher than it was in the liquid. And so in fact, we've enriched the vapor phase. There's a lot more in terms of mole fraction of A in the vapor phase. And that's something that is at the heart of separations. Because if you had started with all liquid, you know what X of A is, right? In that liquid, you made something very expensive and very valuable. Okay, all you have to do now is get this thing to form vapor. And in that vapor, you have something that's really concentrated in A compared to what you started with. So you figure out how to make the vapor. In this case, all you have to do is decrease the pressure, right? Now you have this vapor, which is highly enriched in A. You condense the vapor, now you have A. Or you can use A in terms of in the vapor if you need to, whatever you wish to do. But the point here is that you've enriched A. A is at a much higher composition, mole fraction in the vapor than it was in the liquid that you started with. And that liquid may be what you used. That's your solution pot or vessel or whatever. All right, I went a little bit over, but it's all important. This is a lot of stuff here, a lot of stuff. If you can understand this, I think you're in good shape. All right, so I urge and encourage everyone to really spend some time to understand this. A lot of concepts behind this. Okay, any questions? I wish you all a great weekend, and be safe, and I will see you all on Monday. Okay, take care.
Thank you.
Thank you.
Great.